factors affecting solubility of a soluble salt. There are basically about 3 factors that affect solubility of a soluble salt. The first one is nature of the solvent and solute. Nature of solute and solvent. That's the first factor. These ones are for the soluble salt, not the sparingly soluble one. The second factor is the temperature, and the third factor is pressure. Those are the 3 factors that affect solubility of a soluble salt. I'll begin with the nature of solute and solvent. How does it affect solubility? We are aware that they are what we call polar solutes. And you are aware that polar solutes are soluble in polar solvents. These ones can only dissolve in their corresponding polar solvents. And you're also aware that the non-polar solvents or the non-polar solutes are soluble in their corresponding non-polar solvents. It's very rare or even almost impossible to find a polar solvent soluble in a non-polar, a polar solute soluble in a non-polar solvent. So that's what we can say about nature of the solute and the solvent. How about temperature? In terms of temperature, we should know that the solubility of most salts increases with increase in temperature. For most of the salts, increase in temperature. For most of the salts. However, there are salts that dissolve with evolution of heat. Those ones that dissolve with evolution of heat, their solubility will decrease with increase in temperature. Maybe I can expound more about this factor here, the effect of temperature. In accordance with what we call low Chatelier's principle, which we haven't seen before. We shall see more about that principle in chemical equilibria. So, however much solubility of most salts increases with increase in temperature, if the temperature is in accordance with that principle, which we call the Chatelier's principle. If a solute is in equilibrium with its solution, if a solute is in equilibrium with its solution, which solution must be saturated? The solute is in equilibrium with its saturated solution. Increase in temperature will favor that change that occurs with absorption of heat. Increase in temperature will favor the change which is accompanied with absorption of heat. So the more or less of the substance will dissolve according to which change is accompanied with absorption of heat. So if the dissolution of the solute in the solution occurs with evolution of heat, that reaction is not favored with increase in temperature. It will be favored with a decrease in temperature if heat is evolved. However, if a solute dissolves with absorption of heat, if heat is absorbed for the solute to dissolve, then that solubility will be favored with increase in temperature. That's the key point there. Then the last factor here is pressure. How does pressure affect solubility? So effect of pressure is negligible for a solid. Effect of temperature is negligible for a solid because high pressures are required to affect volumes of liquids and to affect the volumes of liquids. And extremely high pressures are required to affect solubility of solids. However, if you increase the pressure for a given value, an appreciable change in solubility can be seen. And it's also in accordance to Le Chatelier's principle. For example, if you increase pressure to about 500 atmospheres, increase pressure, experiments on solubility show that if you increase pressure to about 500 atmospheres, the solubility of sodium chloride is increased. So you need extremely high pressures to affect solubility of ionic compounds. Although that factor is its effect on solubility of compounds is a bit negligible and not worth to consider in most cases. Now we come to what we call solubility curves. You have come across these curves in your ordinary level. You saw what we call solubility curves in O level. Those are graphs plotted for solubility in grams per 100 grams of solvent against temperature. You normally have solubility of given salts increasing exponentially. For example, if I have a salt like sodium chlorate, that is its solubility curves, its solubility curve. Then you can have potassium, sodium nitrate. Its solubility is below that of sodium chlorate at any given temperature. The most common ones that you saw at O level was that one of sodium nitrate and potassium nitrate. This curve here, it meets that one of sodium nitrate somewhere. That is a curve for potassium nitrate obtained experimentally. And then the one of sodium chloride is always moving somehow like that. We have that one of potassium chlorate moving somehow like this. This one is for potassium chlorate. And then we have that one of those ones are enough for now. I may not consider so many salts. So these for salts that form solution is endothermically, the solubility increases with increase in temperature. So you see that most of these salts, their solubility is increasing with increase in temperature. I have a point here, in case you're given a graph and you're to plot that graph. There is a point where a solubility of some two salts is the same. So salts like sodium nitrate and potassium nitrate have a temperature where their solubility is the same. That temperature is always around 70 something. So I should be 75. At that point, their solubility is the same. So you must be able to interpret these solubility curves and be able to extract information from them in case you're asked. So salts whose solubility decreases with increase in temperature, such as anhydrous sodium sulfate, I was to put a graph of anhydrous sodium sulfate here, you'll find that its solubility decreases with the increase in the temperature. It would move like that. So as the temperature increases, for it, its solubility decreases. So that one, you must be aware that when dissolved in water, there is some heat that is evolved during its dissolution. That's what causes its solubility to decrease with increase in the temperature. Other salts that dissolve in a similar way, whose solubility decreases with increase in temperature. We have calcium hydroxide. We also have calcium sulfate. Now we want to see how we can apply solubility curves. You have seen me sketching those curves, but how are they applicable? These solubility curves are applicable in what we call fractional crystallization. So what happens during fractional crystallization? I'll consider curves of two salts, and we see how their solubility varies with increase in the temperature. The two curves I'll consider here are those of potassium chloride and potassium chlorate. You will excuse my sketch here. I can't be accurate using my whiteboard here. So I may have a curve of potassium chloride here, and I may have that of potassium chlorate moving like this. So that's a curve for potassium chlorate. Its solubility would vary in that format that you're seeing on your screen. So its solubility here is the solubility here is grams per 100 grams. Then here we have temperature in degrees Celsius. Now, when you look at these two graphs, you notice that there is a variation in solubility of the two salts. One of them is more soluble than the other at all temperatures below this temperature here. That is potassium chloride. It's more soluble than potassium chlorate at a temperature below this one here. It's around 85. And above that temperature, you realize that potassium chlorate becomes more soluble than potassium chloride. So the two salts have different solubilities in water at different temperatures. Now, how can we apply the knowledge of these solubility curves here to separate the two salts? By the method we are calling fractional crystallization. So that one is usually done by getting a concentrated solution of the two salts. You get a concentrated solution of potassium chloride and potassium chlorate. That concentrated solution is then heated. And after heating it, you allow it to cool. You have a concentrated solution of the two in water, heat it, allow the solution to cool. Now, potassium chlorate being less soluble at lower temperatures, okay? This is the principle now coming into play. This one is less soluble at lower temperatures. So since potassium chlorate is less soluble at lower temperatures, what indeed happens is that as the solution cools, it is the potassium chlorate that will crystallize fast. as the solution is cooling. So the first yield contains more of potassium chlorate than potassium chloride. As we are cooling, the first yield contains potassium chlorate 5 crystals mainly, and a smaller amount of potassium chloride. So after getting that first yield, what do? You redissolve the first yield of crystals. Remember now, this first yield contains more of potassium chlorate and a little, very little of potassium chloride. Due to the fact that we have seen that potassium chlorate is less soluble at lower temperatures, so it crystallizes fast at lower temperatures. So redissolve this first yield in hot water. When you redissolve it in hot water, you repeat the process of crystallization. You again evaporate and allow to cool again. When the process is repeated after several times, you'll get pure crystals of potassium chlorate 5, which are obtained finally free from the solution. They are crystallized out from potassium chloride. So that's how the knowledge of solubility can be applied to separate a mixture of potassium chlorate and potassium chloride. Have I been clear, friends?
Yes, teacher.
All right. Now, after looking at that detail, we are going to begin the most important part of this topic, solubility equilibria, which is what we call the concept of dynamic equilibrium. Concept of dynamic equilibrium. And then we proceed to what we call sparingly soluble salts. We have looked at detail the soluble salts, factors affecting their solubility, experiment to determine their solubility curves, and application of the solubility curves during fractional crystallization. But before we go there, I'm going to look at some examples of how to calculate solubility and then how to plot and interpret solubility curves.